Hello and welcome to my online video tutorial for the GlobeCom. It's about post-channel communication, breaking the channel limit for 6G. It's a joint work together with Holger Boche, Fitzek, and Rafael Schaefer. I will start with this part one. It's from Shannon to post-Shannon communication. I will present you the basics of Shannon communication and then show you the way to post-Shannon communication. Here I choose a special goal-oriented communication identification. In part two, I will tell you about message identification, known results, about deterministic and generalized identification, and I will present you general post-channel communication tasks. In part three, I will explain you how resources help to increase the capacity and the rates of post-channel communication. Part four is about embedded security, and part five about further implementations and identifications in networks. Let's start with part one. So Claude Shannon defines the following model. Somehow we have a message as a transmitter. The transmitter sends something through a noisy channel. The receiver receives something, and the goal of the receiver is to find out which message has to be sent. So he makes an approximate of the message the receiver sends. And of course, the goal of the receiver is that the probability that the message is equal to the sent message is high. So that was what Chen was thinking about when he said the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. Let's do it more formally. So we look here at Shannon channel coding theory for discrete memories channel. He modeled this in the following way. We have here Alice, which have messages from 1 to n, and she wants to send this message over a noisy channel to Bob. So Alice uses a block code, so she can choose symbols from 0 to q-1 of length n to send it over the channel to Bob. We have a channel, and the channel is nothing more than a stochastic matrix, which can change the symbol because of this conditional probability. We assume that the channel is memoryless, so if we send a message xm, the probability to receive yn is just the product of all the single probabilities of each symbol. And so Bob finally receives a word in yn. And the goal of Bob is he wants to decode the correct message with a small decoding error. So he wants to find the correct answer to the question, what was Alice's message? To define this, we define a deterministic code. So in a deterministic code, Bob maps a message, so each message belongs to a code word. Here I denoted it by UI, and this UI is of from the set x to the n. That's the coding alphabet. And then we have decoding sets di in yn. That means if Bob received something in the screen area, for example, he assumed that he has received something from yn. Because we assume the channel is noisy, it cannot be this pointed generally. Then for this reason, of course, the decoding sets have to be distinct. And of course, we want to shoot the system in such a way that this probability, the error probability, is small. And here you see again, Bob decided that message I was sent if we receive a word in DI. The question is now, which of these triples are possible? And observe, we have two conflicting conditions. On the one hand, we want to have very many messages, so we want to have m large, and at the same time, we want to have lambda small. The way we want to look at it now is in the following. We denote it by m and lambda, the maximum number of messages that can be transmitted over a channel for a given word length n and the probability of error lambda. This we denoted by m and lambda. And in its fundamental theorem, Shannon proved that m and lambda grows exponentially in n, and moreover, he proved that this limit here, the limit of n to infinity of the logarithm of m and lambda over n, exists and does not depend on lambda. So Shannon defines this limit as the capacity of the channel. So you see it here again. As a reminder, I draw here the channel again. So this is the message of Alice. This is the estimated message of Bob. And Shannon shows that the capacity of a discrete members channel is equal to the maximum over all probability over all random variables x, such that the mutual and about the mutual information between x and y. And then we can recover exact the message m with an error which goes to 0 if n goes to infinity. I just noted here that in this case we don't use randomness as the decoder. We try this later. So it's the next step. What is now if we allow randomness? First, Bob has some randomness at the sender, and he can use it. Then we can define a code, a transmission code, in the following way. Instead of having here a UI for a code word, we have a UI for a probability distribution on the code words. That means in each, if Bob wants to send message I, instead of having an exact map to a specific code word, he uses a probability distribution and then randomly selects one of the code words. So Qi should be a probability distribution on X and on the complete, sorry, not only on the code word, on all possible sequences we choose this probability distribution. Of course, all the other things are the same. The decoding set should be still this young, and we also want that the probability of success should be big, or the lambda of error should be small. And then it was shown that a deterministic transmission code exists if and only if a randomized transmission code exists. That means in this case, we do not have any advantage by choosing a randomized code. So in terms of capacity, there's no advantage in this case. Now let's come to the first, the simple Post-Shannon scheme, which is identification. So here we have Alice again. Here, as a reminder, I have the set of the transmission scheme of Shannon. And now here I have the scheme of the identification scheme of Alswede and Deppe. So in this case, Alice wants to send a message again over the channel, but the decoding is now different. So Bob has just one message. Here it's message J, and he just wants to know if Alice had sent this message J, yes or no. So he made a test, and he just wants to have a binary answer, yes or no. It's like a hypothesis test. Of course, the encoding has to be changed in such a way that Bob can do this decision in this way. And of course, we assume that Alice do not know in beforehand in which message Bob will be interested in. Otherwise, it's easy. So, how will this scheme now change the capacity? And this I will answer in the second part. So we will look at, in the second part, of message identification and a little bit more general post-Shannon communication tasks. First, I will start with this deterministic identification. In this case, we just have one code word per message. Then you will see that in this case, randomized identification gives you an advantage. And this, and on here we have to information theoretic analysis. And here I will show you how one can construct identification. And finally, I will tell you something about general post-Shannon communication tasks. I will explain you what K-identification is. Then in part 3, we come to new resources. We will speak about identification with feedback. How does feedback help or improve the rate of identification? You will see that common randomness plays a very important role for identification. And therefore, I will explain you how one can generate common randomness. Then we will talk in part 4 about embedded security. First, I remind you what for transmission it means to have embedded security. That's a wireless channel, which were first introduced by Weiner and later by Schaefer and Kerner generalized. Then I will explain you how we can generalize this for identification. And you will see that the formula will change. Of course, we want to make also our model robust. So perhaps we have a jammer also. And so I will speak about secure and robust identification. Finally, in part 5, I will explain you how identification works for a broadcast channel and how post-Shannon theory in general can help us to develop our theory for networks. Okay, now we want to continue with part 2, message identification and general post-Shannon communication tasks. The story starts with the problem of Yaya. It's in communication complexity. So he assumed the following. He considers the problem that Alice and Bob have an integer between 1 and 2 to the n, and they are connected with a binary symmetric channel. And this is nothing more than a discrete numbers channel with binary coding alphabet and probability from 0 to 1 and 1 to 0 is equal to p. Now, Bob wants to find out if he has the same number as Alice. How can we do this? So the first idea is very simple. We know because of Chen now we can transmit with an n lambda code. So block length n, m messages, which is equal to 2 to the m in this case, and lambda is the error probability. Bob decodes the integer and compare it with the integer. And the first result of Yaya is a decoding problem. He showed that for this protocol, the so-called decoding problem, for any given large constant mu, there exists a p0 between 0 and 1 over 2, for which no scheme required less than mu times n bits. Can guarantee for large m any bound smaller than 1 on the error probability. That means it's not possible to have a linear number of bits, so mu times n bits is somehow not possible. He thinks perhaps it's possible if he changed the model. And the second idea is somehow he doesn't restrict Bob to decode the message. So now the goal of Bob is to decide if his messenger is the same, yes or no. And this is called identification problem. And there he showed that for an arbitrary given small constant gamma and p again between 0 and 1 over 2, the identification problem can be solved with 1 plus gamma m bits. So we can do it linearly, merely with m bits. So the identification model, the identification problem is much easier than the decoding problem. And the idea was, in principle, the protocol Alice chooses number I, Bob chooses number j, and now they want to know what is the value of fij. It's 1, if it are the same, and 0 otherwise. And Alice can transmit a code word with 0 and 1 of length n to Bob. Bob receives this code word and wants to determine Fij with small error. And in the encoding, Alice sends UI for message I, and the transmitter sends its code word. Later we will come to it when we think about communication. You will see that we somehow use a typical encoder. And for decoding, it's very easy. You see, Bob just uses a distant encoder. And we can, through and using this protocol, Yaya showed that it's possible to do it by 1 minus gamma times m bit, that we just need 1 minus gamma times m bits. Now let's come to the communication problem again. We can use this protocol now also to communicate. Instead of using it for communication complexity, like Yaya did, we can ask what happens if we do this encoding, sends UI over the channel, and Bob just want to know, is it my message, yes or no? In this part, we use deterministic mapping for coding and code size of 2 to the NR for the DMC. And we will see that the achievable rates are higher than in the transmission case. Again, we defined, if you remember what we did in the very first part, we defined a transmission code like Shannon did. Now we define a DI code, deterministic identification code. So here we use LNR, that's the code size, it's a special notation. Later you will see why I use this notation, because here you see also how the messages are growing. So we assume that they grow with 2 to the NR. N is again the block size. And now we have two kinds of error, lambda 1 and lambda 2. Why do we have these two kinds of error? Because we no longer assume that the decoding sets are disjoint. We just assume that decoding sets are subsets of y to the n. We can do it also because later I will explain you how we can generalize it to the Gaussian channel, and therefore we consider it already with some power constraint, or some input constraint for the discrete numerous channel. So we make the assumption that we have a function phi which gives a value to every code, to every symbol here of code words, and then we assume that the total sum is the average of the total sum is limited. I told you we have now two errors. The first error is the same we have already in the case of Chen, and the second error is now special. That's an error which happened because of the decoding. Because this decoding set are no longer disjoint, therefore they can overlap, and then sometimes an error could happen. Call this error of type 2. And the first theorem we get is when W of a DMC is the transmission matrix with distinct rows in the channel matrix. So it's really necessary that all rows are distinct. Then the DI capacity under input constraint is given by this formula here. You see, we take the maximum of all Px, and here we have the entropy of x. So it's much better than in the channels case, where we have here the mutual information. That was our result, and from this result, already Alswede mentioned in his first paper for deterministic identification for the special case, we have logarithm of x, so that's without power constraint, but a proof was not provided in this case. But now we proved it because we can just choose, of course, our power constraint in such a way that we allow every word. And then we get immediately also, if you look here, then we have here the entropy, and of course, that the biggest value the entropy can have. So we also proved the result of Alswede. Later, Alswede and Chai generalized this model for a compound channel, but they based on this result. So the basis for their result was this result, and so this paper is only true by using really this result. So the idea of the achievability is very similar to the result of Gaia. So the idea, somehow it's a combination of Yaya's ideas and Isaac's ideas. So as I told you, what we use here is a typical encoder, which you know perhaps from Shannon theory. So given a message I, we transmit an xn, which is in the typical set of px. And the decoder, he chooses here, it's different like in the Yaya case. Later we will see when for the binary symmetric channel we need just a distance decoder, and the same is true also for the Gaussian channel. But if we look at the general discrete numberless channel, we need a typical decoder. So like it's often in information theory, he chooses yn such that vj and yn are in the typical set. And then we have to do the error analysis by standard type plus arguments. We will prove that the error of the first kind go to 0, and by conditional type intersection lemma, we can prove that the second kind of error goes also 0. So somehow it's just an extension of the Yaya approach of the non-binary channel and to the bound of the type 2 error. So the converse, I will not go into details, but the main thing here, how to prove the converse, is very easy, because we just see we cannot have the same code words for different messages. We have to use different code words, and then we count the number of possible code words, and of course this restricts ourselves to the number we have. So this is the basis for the converse. Now we want to generalize this to a more realistic channel, that's the Gaussian channel. So we assume that now we have a Gaussian channel with wide Gaussian noise. So the encoder can send real numbers, a sequence of real numbers, and the decoder has again made a decision, which was to send messages. And of course, our signal have additive noise, wide Gaussian, and it's a realization of a wide Gaussian process. And of course, to make it realistic, we use the power constraint. That was the reason why we proved the result for the discrete memberless channel also with some kind of power constraint. And we can show that in this case, if we look at the capacity is infinity. The idea of the construction is somehow really easy, because we choose here a sphere because of the power constraint, and now we pick the code word. So each code word is surrounded by a sphere, and we look how many spheres can fit into this big sphere here. So somehow we do some sphere picking. Later we have to see, of course, we have to adjust the radius of the sphere because of the error of the first and the second kind somehow. So we have two radius, and you have to play with it to show that everything works. But the main thing is, in principle, to do sphere picking. And now for the encoding, given a message I, we transmit some UI of this sphere there. Let's assume we have the sphere picking. Later we speak about the radius. So and for the decoding, you see here it's much easier. We don't have to use even a typical decoder. What we need here is somehow just a distance decoder. And you see, when we use this scaling here, the normal scaling, we get that the DI capacity is infinity. But if you use, perhaps the scaling isn't bad, so we can look at this scaling here, but then it turns out that the capacity is 0 then. I have to talk with Andreas Winter, and he tell me why don't you choose the scaling in between? So even we didn't first look at this scaling because it was clear that it goes to 0. But Andreas, I just explained him this result here, and he told me just look at other scalings. And what is the correct scale then? And then we have the idea to look at this scaling, to scale the number like 2 to the n log. So n to the n somehow. So such a scaling. And if we look at such a scale, really we get a finite number for the deterministic identification capacity. And we can prove that it's between 1/4 and 1. We just have to plug in this new scaling in our old proof, and we immediately get this two bounds. Unfortunately, we were not able to prove it exactly, but our conjecture is that 1/4 is correct. And I talked to a colleague, he's working on this, and we perhaps in some months we will have a proof for it that this is really the truth. And of course, we see for the other scalings, for this scaling it's infinity, and for this scaling it's 0. So it's a nice result, and we get a new scaling. So it's important to change the scaling to get here new values. What is really important is here, if you look at this result and compare it, if you know information theory and compare this with the result on information theory, what is with the Gaussian channel, then normally the capacity always depends on the SNR. So the signal to noise ratio. And here, no dependence in this. That's really surprising. You can generalize it now. So what we do is somehow we also generalize it to a model with two models with fading. First, we start with a slow fading model. So in this case, we have extra continuous random variable g. You see here, it happens because of interference or something. You have this extra random variable g here, and the transition power is limited to this value, to m times a. And what is the result? And we get a really similar result here. We get in principle the same. For slow fading, you get the capacity bounded by 1/4 and 1, and again you have to change to this scaling. Furthermore, we also generalized it to fast fading. So in this case, G is a random sequence of fading coefficients. Z is, of course, as before, an additive by Gaussian process, and we can look at this model with fast fading. And again, we can show the same result, no dependence on SNR, and again, these two bounds, and hopefully soon, so our conjecture, let's say it's a conjecture, that this is a true sum. So where can we use deterministic identification? And one application we find out by talking to people from biology and to Robert Schober, that molecular communication could be an application. So we want to find out how molecules communicate with each other. And somehow what the people do, they saw that there are higher rates than expected because they model this with a channel model. And why could this happen? And the one reason could be that they are eventuated. And so we can establish the DI capacity for such a model for molecular communication. And a model for this communication between the molecules are the discrete time Poisson. And we have there also a power constraint. And that was our first step. We considered the I for molecular communication. You see, we have here Poisson distributed random variables, and lambda is the expected number of interfering models. We have this rho x as expected number of observed molecules due to the release by the transceiver, and yn the output vector and the power constraint, and now the probability to to receive a Y at UI send is depend now on the Poisson process. And in this case, we also get some bounds. So again, we use our method and find out that in this case, we have it about 1/4 and 3/2. We have a paper on archive, so if you there we explain a little more how the Poisson channel and identification relates to molecular communication. Again, you see, we use our method somehow. For the achievability proof, we again use the sphere packing. We only have to choose the radius in a correct way, and then can prove this value here. So we also use Minkowski-Laka theorem because of the traffic packing. We need some density here, and then we can estimate here the rate. To prove that the errors go to 0, we just use Chebyshev inequality. Now, that was just a quick reminder, is quick thing to show you that we can apply discrete identification, a deterministic identification to molecular communication. What we also have now, I want to look now at randomized identification. If you remember from part 1, randomized identification doesn't help the encoder somehow in the case of transmission. Now we want to know, does it help if we look at the same model just for identification? And that was originally introduced by Alfred and Deppe. And they established the capacity with randomness at the encoder. So that means now, if you remember the definition for deterministic identification code, we changed it here like we do it for the transmission code, that instead having here a UI for a code word, we have a QI for a random variable or for probability distribution, such that Bob can randomly choose a word from XN. And again, we have error of the first kind, it's a channel noise, and of the second kind, it's the ID kind. And you see it somehow here, I wrote randomization is crucial to establish capacity. What does it mean? Yes, if you see it here, what we can do now is, let's assume we do a random experiment on this code word in the green circle, and then Bob sent her at one time, he sent this part, at another time he sent another word in the green circle, and so on. And furthermore, we have at the verifier, we have also this VIs, this region here, which can overlap. And so in this case, ID doesn't require decoding, it requires only encoding, because sender and verifier are identical. So code words that overlap and don't have to be convex like it is here, but they can be N somehow. And here, to remind you, I show you the difference. That was a picture I showed you in the first part for the case of Chen, and now we have something like this. And now you will see immediately, you will see soon in the next slide, I think, that we have a double exponential grownness. So at first I want to show you that there are different kinds of errors. You can have a correct positive and a correct negative thing. So an error can be also depend on decoding. We can land here, but you want to know this identity. In principle, we don't have an error because it's landed in the green circle, but it overlaps with this circle and therefore makes an error. So that's error of the second kind. So you see here, you have these two errors here, type 1, noisy channel, channel coding, and removed by channel coding. to two-error overlapping code word identification. And what was very surprising in the first thing for Alfred and Dick group, that the capacity is the same. But you see, you have another scaling here. So now we have double exponential code box size. Instead of looking at 2 to the n r, they looked at 2 to the n, 2 to the n r. And then they find out that the same that we also get here is the Shannon capacity. How can we achieve this? How we can achieve this big winning? So the idea is the following. I think I have a picture on the next slide, but first I want to explain it how it's written here. So what we use an index set of colorings of m, which is a relatively small number of colors, 2 to the n. And both is known to the sender. And the sender chooses now one coloring at random, say t. That's a coloring function. This coloring t goes from the index set to the color. And every message gets a specific color. And if now we want to transmit message I, so he maps every identity to a mapping. That means, let's look here, he calculates the color of message I under T and transmit both the index T and Ti. So that means if you want to transmit identity, you choose a coloring function T and choose randomly a message I with equal probability and then look which is the color of that, and then he transmitted both random selected message and the value of Ti. And now the receiver, he said, here's another I prime. He also have a function Ti prime, and you want to know if his I prime is equal to this I. So what he did, he first decoded the random chosen message of the sender first, and put it in his function and compares the two colors. If they are the same, he said, yes, it was my message. And if they are different, then he says, no, that was not my message. Here it's, you see it again as a picture. So this is the coloring function, Ti. We have here the coloring number L and the color. So again, what does the sender do? So let's assume we want to send message I. We select this function here. Then we randomly choose one message here. Let's say L. Then we put it into his coloring function Ti of L, evaluated it, and he sends L and TIL to, and he sends L and TIL to the receiver. And the receiver, of course, he has another function, and he can calculate if this function on L has the same color. Yes, he said it is my message. If no, he said it's not my message. So that's somehow how they do the directory. They just show the existence of such kind of functions, such that error of the first and of the second kind goes to 0. For the converse, there's some history. So Alfred and Dick, they just have a soft converse. So this is somehow less than a weak converse because it requires that the error goes exponentially fast to 0. So it's an additional assumption. For a weak converse, you just assume that the error goes to 0. But that was the only way how they can do the converse. Then Hahn and Verdi came, which is a method, it was called method of types, and they can do the converse. In principle, what was hidden there is already what theory of resolvability. That was somehow the third proof, so they Hahn and the second proof. It's a more concrete analysis, and I think here was a little error in it. It was corrected, but this is a more clear proof. And there was a nice discussion between Badu and And Altswede because they use analytic methods, and Altswede told them it must be possible to do it with combinatorics. And somehow they dared, so that is that it's not possible. It's so difficult. It's not possible to do it with just with combinatorics. There must be some analytic in it. But then later, people get some kind, also use the idea of Hamlet, but in a combinatorial way. It's combinatoric resolvability, and he can also prove the converse by himself with another method. So what do we have? So we have here this message transmission. We want to recover the exact message, and we have the channel capacity equals to this formula, which was found by Chen. And we have this size. And now if you look at the identification, I should give a randomized case of Altswede and Glück. In this case, we have the same result here, and we have 2 to the NR messages. So double exponential. The surprising thing is that these two capacities are the same. And of course, now we can ask, can we also have some phenomena like in the deterministic case when we generalize it to the Gaussian channel? I write it down here already for the minor Gaussian channel, but of course it also holds for the Gaussian channel. And you see, in principle, you get the same rate if you know the result for transmission as in the transmission case. So in principle, there is no win like in the deterministic case. Because you assume again you have a lot of randomness at the sender, and this gives you so much that it doesn't help that you use a Gaussian channel. So in principle, you get the same capacity as in the transmission case if you change from the determinist from the discrete case to a continuous case. For the single case, we have the converse. For the minor, the converse remains still open. So what we did now, until now, we showed the switchability just by existing proof. The question is, can one really construct also this code to make them usable? Because you know, also Chen's result doesn't really help to construct codes. It helps a little bit for the ideas how one can construct code and which kind of code exists. But it doesn't construct the code really. So what then later I know in transmission you would say, okay, but we have polar codes and they achieve now the chaining capacity, but the first proof was just existing. And also here, so Han and Badu ask themselves, is there an idea to construct R icons? In principle, what we have to do is construct these TIs, which I showed you, which is the main idea for the construction proof. And let's see, that's really possible. What is the idea? The idea is, of course, we construct now such functions. So just as a reminder, sometimes it's also not bad to call this coloring tags. So because you tag them at the end, you make a tag at the end. So the TIs, the small TIs are the same like the big TIs. They go from M to Q. So and now how to encode? We have an M and an TI. We have an encoder, and we want to accept or reject the message. So again, so TI of X, the second part of the message, should be sent without using capacity. Now, first we must have a capacity achieving transmission code, and then we can use it to achieve the identification capacity. By using such a tag, labeling, or coloring function TI, which has the following properties. So we want to construct now such MTI of M, which I showed you before, in such a way that we achieve the identification capacity. Therefore, we define now a tag code, which is I, M, Q, and omega M, in such a way that the size I is exponential in M. The bits of the output log Q is sublinear and bits of the input log M. And it goes asymptotical by 0 by epsilon. And how can we do this? And the idea is the following. To have this tagging function, we can write them as a table. So let's assume this is my first function T1. I can write the value of T1 here of if I put in a 1. If I put in a 2, I write the next one here. And if I put in an M, so because we have M different messages, I put the color for each message here, one after another. And I do it for each tagging function, from C1 to Ci. And you see, I get here a matrix. And what I want here is I want to have a distance, because we know that this tagging function should not overlap too much. That's the reason why we want to have here d is equal m minus omega. And in principle, what we need is somehow that log I over log m goes to 1. That's they grow double exponential, because that's more or less the block length. That this part here goes to 0, that means the final part doesn't count so much. And this d over m should go to 1. Then we can find a code, an identification code, which achieves the identification capacity. And you see here already, this reminds you perhaps on something. This here is nothing more, or it's already written here, than an error correcting code with this distance here. That means we just have to find something which already exists. We have to find error correcting codes in such a way that they fulfill these properties. The question is, do such error correcting codes already exist? Oh, okay. First, I want to show you if I have all these properties, one can really prove that we then achieve the capacity. It's just the Gilbert-Boston. So it's just this reconstruction. In fact, you start with one code, make a sphere around it, and the next one, and so on. So we know that at least such error correcting codes exist, or such tag codes exist. And then how to use this tag code? Before to think about which tag codes we can need, we have somehow a sender ID, an ID encoder. Here we assume we have a noiseless channel. Here's the question, is it equal? And an ID encoder again. So we can consider it for the noiseless channel. So that means we concentrated just on the error of the second kind. And then, of course, finally, we can insert here somehow on the Shannon system, we can run an ID encoder. So we have here an ID encoder, and we send the randomized selected message over this noisy channel, which can be regarded here as noiseless, because we know of Shannon theory how we should select this, and then we just do our ID encoding. And you see, in principle, what we do, we have here some local randomness, and the main part is to send this local randomness through this channel to the ID encoder, because that's the first part. When we select randomly the message, that's the only part which really counts. So the other one part, where we send the color, have capacity 0. Somehow what we do, later I will come to it in more detail, we generate common randomness. So common randomness is very useful. If someone gives us common randomness, then it would be nice, and we can directly do identification with only sending the color. So now you see what we do here. Somehow that's our table here, and we have to use it to send it, and also to send the random tag. So we have here again, here's a picture how we can choose it, the random tag. position, and then in the second part, which is more or less nothing, we just send somehow this tag, this value of the tag here, and he compares it with his value, and then he says yes or no. Okay, here you see it. Oh, sorry. Here you see it. Perhaps you have here the ID 24, and here you have the ID 37. And for example, you see if both chooses, if the sender chooses the 0 position, then you would say, no, it's a different value. Okay, it's not my ID, everything is fine, no error. But here you see the error of the second kind. If he chooses a 31 position, and you see here, this ID has color 9 here, or tag 9 here, and this ID has also tag 9. So then an error of the type 2 happens. How to realize this? So first thing, I read Solomon code. That was the idea of a do and they. Oh, no, I think that was wrong first. The do and they did this construction here. They show that it's capacity achieving, but somehow we used it then with the student, and we want to find out, can we use this code? It's a very nice result of a do and why, but until the error runs to 0, you need very big code. So the message set must be very big. And then you have a long computation just to compute your big matrix, or because you cannot store it. It's so amazing big that that you cannot compute it before, and so you have to compute it if you receive something, and somehow they are not really useful. So we goes then to different codes. We try out turbo codes, and even these are first thing, they are not capacity achieving and not good for finite lengths. Then you try with the Miller codes, and the first theoretical result, they are also capacity achieving. It's a little bit more simpler than perhaps this construction here. And for finite lengths, they have better performance. So it's even usable. We are still fighting a little bit with, we already simulate them, and we also have some implementation, but it's already still very slow. We try to improve the performance. And we work on further possibilities like polar codes and randomized codes. Finally, in this part, I want to explain you that we have also more general post-Shannon tests. So I start with the most simple, with the identification. So we only want to have one property of the message. So we only want to say, no, it's my message, yes or no. But we can also look at the so-called K identification. And this is more generally. In this case, so K identification is a generalization of the standard identification. Instead of one target for message J, we define a set S, and it has J1 to JK. So K many selected messages which the decoder is supposed to identify. So instead of interested in one message, he is interested in K message. So even if you are in a if you look at this in a goal-oriented way, you will see perhaps he's interested in K property. And we express this by looking at this achievable rate pairs, R and kappa, where R is the second order rate, it's again 2 to the 2 to the NR, and kappa represents the first order rate for K identification. And then already Altswede shows that there's a lower bound, R plus 2 kappa, for the capacity is bounded by the capacity where this is again the Shannon capacity of transmission. We start also work on it, so even Altswede it was not possible. We find also an upper bound and a lower bound, but they do not match. But perhaps K identification is somehow the next step to look at construction. And of course, there are constructions based on identification codes, but they are not really developed yet. Okay, this finished the second part. So, what do you do? If I do not need to decode the message, there are alternative coding schemes. And identification increases the transmission rate for deterministic and for randomized identification. And the identification rate for channels with local randomness grows already double exponential. And of course, we should consider post-Shannon paths more often. Okay, let us continue with part 3, exploitation of new resources. The first resource we want to look is feedback. So we assume the following. We do now deterministic identification for a channel with feedback. Before we do this, I want to remind you, for transmission, Shannon showed that the feedback capacity of the discrete member channel is the same as the capacity without feedback. So if you have noiseless feedback for a transmission channel, noiseless passive feedback, then the capacity do not increase. So it means in the case of transmission, it doesn't help to have this feedback linking. But now, how does it affect identification? So first, let's start with the result of Alfred. They considered the discrete members channel, and we extended them with the result to this Gaussian channel. So the result from Alfred is as follows. The capacity is equal to the maximum of the entropy of the output distribution here, if the capacity of the channel, the transmission capacity in this case, is bigger than 0. This capacity is 0 if the channel is noiseless or the capacity is 0. And we again look at the double exponential scaling. That's 2 to the 2 to the nr. The first thing which might be very strange for you, if you look here, when does this increase? This increases if the channel is more noisy. That means if you have a noisier channel, it helps you much more than a noiseless channel. You see, even for the extreme case of a noiseless channel, the capacity is 0. In the first view, that's very strange. But if you remind yourself what we have done in the part before, then there was something with common randomness. Common randomness helps a lot, and the main part of identification codes for the reachability part was to create common randomness. And therefore, the idea of Alfred was just to use the noisy channel and the noiseless channel to create common randomness. So that means if your channel is more noisy, then of course you can create more common randomness because of the noiseless feedback. You cannot do anything if the channel is totally noisy, so it's capacity 0. But otherwise, if the channel is noisier, you get a bigger capacity. So that's the reason noise can increase the identification feedback capacity. We generalized this for the Gaussian channel. So we looked at the Gaussian channel, the same model with noiseless feedback. We use a normal notation here. The channel is now noted by sigma square. Everything is Gauss distributed. And we define again MN lambda 1, lambda 2 code. LNR, because of the scaling, you know that's important even. So N is block length, lambda 1, error of the first kind, as normal for transmission, lambda 2 is the error of the second kind. And of course, for the Gaussian channel, we need some power constraint. And then the feedback strategy, that means that if we send something, it always depends on the received symbol, which were received before by the decoder or the receiver. Again, the decoding sets are not disjunct, so they can have overlaps. And Fn denotes the set of all encoding functions. Fi, where A1 is just an element of X because we haven't sent something before, and Fit depends on the method, of course, and additionally on the before received sequence, which are now known to the sender. And the theorem what we get, even if we look at double exponential growness, like we do here, the channel capacity, the channel identification capacity is infinity. What can we do? Can we do something similar like for deterministic encoding, where we change the channel and get some finite here, some finite value here? So we know without feedback for deterministic identification, we have this growness, but even if we change it, it doesn't help us. And that's in general is good. We can use any scaling, and this doesn't help us. So that's very surprising. So we can use 2 to the 2 to the 2 to the 2 to the n r, and it still gives a finite, non-infinite capacity. But if you now look at the proof, at the shiftability proofs, then you will see why this is the case. If I just remind you about our construction we have before, also for the discrete case, with our coloring function or hanging function. So in this case here, we have again our number here, our ground set from 1 to L, and our coloring set from 1 to L. And what is the idea now? The main idea is it's enough to send one symbol to create as much randomness as we wish. Why is it possible? We send here x equals 0, and then we get here Gaussian noise. So you get here some noise, some real number, and it's going back via the noiseless channel. And therefore, we can already create infinite randomness just by sending one symbol. And this we can use if we can choose any L depending on our scaling. With one symbol, we just can randomly choose one of the symbols, and the rest, the n minus 1 symbol, we can use to send the tag to the receiver. And that works. So that's written here. So we have 1 plus m here and then we can use it for the tagging. So again, we have the same procedure. One symbol, infinite or as much randomness as you wish, depending on the size of your L, and then just send the tag, and the receiver decided yes or no. That's a solution for this theme here. And therefore, we can create infinite randomness just with this channel model. There's also a funny story behind this. We first have a achievable part, which was not infinity for some scaling, and we tried to find a converse, and we were not able to find the converse. We tried different things, resolvability theory, and all this part. And then Rafael, one of the co-authors of this, also speaks with Moritz Wiese, and he tells us, are you sure that your direct part is correct? And then we find this part here together with Moritz, and now we know there is no converse. So if you look now in general at the coding scheme, you see I will not speak today about effective secrecy or covered communication. There we have this scaling here. We have here deterministic identification. We have here deterministic for the DMC, deterministic identification for the Gaussian channel, then covered identification, we get this scale here, then we have randomized identification, and the IRIS feedback. So the scaling, you have to change the scaling if you look at different things, because normally you look like just at this scaling, but this doesn't help you for the rest here, then you always say infinity, the capacity, and here, then you cannot, not really know what is going on. So it's always good to look at different scaling. You already noticed that common randomness is a main thing of identification. Therefore, it might be also useful to look how we can generate common randomness. And this was done by Fitzek and Schaefer. So the goal is you have two sources. They assume they have a noiseless channel which can transmit messages with rate R from Alice to Bob, and they want to, Alice gives out a number and L gives out a number, and they want to have this, that these numbers are the same. Yes? So they create common randomness. You see immediately that's something you can use for identification, of course. So here are some known results, which are already known. And the definition of common randomness is as follows. The common randomness capacity is the maximum number nu such that for constant C greater than 0, epsilon greater than 0, and delta greater than 0 for all sufficiently large, there exists a permissional pair K and L of random variables of length n of the set K, such as the set kappa is smaller than e to the Cn, such that the probability that K is not equal to 8, that's the error probability, smaller epsilon, and h of K over n is bigger than mu minus delta. So, if the sender and receiver have a common randomness capacity CR, then by the so-called square root n trick of Alswede, that's a transporter lemma, that's somehow using text. So it's really the same what we do for identification. We have that identification capacity is always bigger than the common randomness capacity, and if the identification capacity is greater than 0. This holds for the discrete memoryless channel and for memoryless channels. And for many channels, in particular for channels with feedback, quality of feedback, it seems to be plausible that common randomness and identification are very near together, and Alswede even conjectured that, or it's not here, that these two capacities are the same. But that's not true, so he found counterexamples. Why we want to use common randomness? The first thing is identification. I will come back to it again in the next slide. But there are also other things where common randomness, not secret common randomness. Of course, if you have secret common randomness, that's another thing. Then you can use it for key generation or as a key directly. That helps you for cryptography and all the things that I think that's immediately clear. But what we have here now, we don't care about secrecy. We just create common randomness and want to use it. Where we can use it, we know already for transmission, we cannot use it, but can we use it for other things? The first thing where I come to this later is called random coding over arbitrary channels. There we can use common randomness. It's useful. And of course, common randomness can increase identification capacity. Let's look at what is an arbitrary channel. An arbitrary channel, let's look at an arbitrary discrete memoryless channel case. Oh, let's look at this case. So you have a sender and a receiver, and perhaps you have a jammer. And the jammer can do the following. He cannot cut the whole line, but what he can do, he can influence the channel so that it changes. So every time you send a symbol over the channel, he can choose another channel in a set. And every time the channel is changed. And this is called an arbitrary weighing channel. So the good thing is we know the set of channels. It can be even infinity, but we know it, and we want to have a code. We want to know the capacity first. That's the most thing. And how can the gamma? It's somehow like a game, because we're looking at the worst case. The gamma want to avoid that the sender and the receiver can communicate. And what can he do? The problem is there are cases where he can symmetrize the communication between the sender and the receiver. What does it mean he can symmetrize? So somehow the sender, as the gamma, can simulate the transmitter. He shoots just the code word X prime and passing it through the channel to get a state sequence S. And the decoder is unable if the transmitted code word was X and X or X prime, because every channel is symmetric between its two inputs. So you can somehow simulate another thing. So that means at this point the capacity falls down to 0. So somehow what the gamma can do is a so-called denial of service. If you look at this capacities formula, they are very funny, because you have a capacity line and it falls down to 0. It can only, the person stays there for a while and then it goes up again and the capacity continues. It's a very strange behavior. And of course, the gamma always want to go to the region and influence this channel in this, in such a kind that we have symmetrizability. But how we can avoid it? And that's very nice. There exist protocols that we can add randomness in such a way to the protocol that the gamma cannot symmetrize anymore. That means only using the randomness which have sender and receiver, we can run a randomness generation, and then we can run a protocol. Such a denial of service attack is no longer possible. Of course, that's what I told you. Let's go back to identification. Here we have this conjecture of Altswede that randomness capacity is equal to the identity capacity. We know it's true for DMCs, but unfortunately they are a counterexample in general. For example, for channels with memory. But in general, additional randomness increases the identification capacity. You know, if you look at the construction with our coloring or tagging functions, by adding more randomness, we can increase the set of the basic set of this function, and then of course we increase with this the number of messages, and therefore we increase the rate and we increase the capacity. Okay, the problem is what happens if you consider identification with a gamma. Now, if you add a common, we want to avoid symmetrizability. But how to do this? Because we add randomness, what is better now? Should we use it to increase the identification capacity, to remove the symmetrizability? Everything is better than 0. What to do? And we are really lucky. To remove the symmetrizability, only randomness capacity or capacity 0 is necessary. Only a few randomness is necessary for the protocol to avoid the denial of service. And therefore, we can use only such a part with capacity 0 to remove the symmetrizability, and the rest can be used the main part can be used to increase the identification capacity. Therefore, Altswede and Schaefer started with a theory of creating randomness. So they looked at a model where terminals are allowed to communicate over a classical perfect channel. And they assume that this perfect channel equate R, or they can commute about a noisy channel also with weight R. And single letter capacity for both cases were derived. And the capacity is defined as the maximum amount of shared randomness available per channel. And the formula is the rate is R of the channel, then we can reach the following common randomness capacity. It's mutual information between U and X, so U is auxiliary random variable in the Markov chain of U, X, and Y, in such a way that the mutual information between U and X minus the mutual information between U and I is smaller equal than R. What we did, we looked at correlated sources and a general channel. So in our case, PXY, we have discrete members, multiple sources, EMS, with two components, with generic variables X and Y, and alphabet X and Y respectively. And the DMS emits identical examples of X and Y. Now we have the following situation. The output of X observed by terminal A, the output of Y by terminal B. And the joint distribution is known to both. And we want to have common randomness again. And more, you see, I didn't tell it to you, but of course, what we need for identification is uniform common randomness. So, terminal A can now communicate with terminal B over an arbitrary single user channel, defined as an arbitrary sequence of n-dimensional conditional distribution, the so-called generalized general channel, from Tn to Zn, where T and Z are input and output alphabets, respectively. There are no other resources available, no local randomness or something like this. What do we do? So, what we do, we form a function P that maps Xn into a random variable k with alphabet k, satisfying that k is greater or equal to 3, and generated by terminal A. And a function lambda that maps Xn into the channel input sequence Tn, that means from T1 to Tn, and a function C that maps Yn and the channel output sequence into Zn from Z1 to Zn, into a random variable L with alphabet k generated by terminal B. Such a protocol introduces a pair of random variables k and L, whose joint distribution is determined by PXY and by the channel W. And such a pair of random variables is called permissive. And now this U stands now for uniform common randomness. So we call a sheet-will uniform common randomness rate A. Number H is called a sheet-will uniform common randomness rate if there exists a non-negative constant C that for every alpha, beta, and delta bigger than 0 and sufficient large N, there exists a permissible pair of random variables of K and L such that the probability that K is not equal A is smaller equal alpha, that's somehow the error probability, that kappa is smaller than C2 to the Cn, then that this difference 1 over n, and the entropy of K minus 1 over n, kappa is smaller than beta, that's somehow this is a uniform, that it's uniform distributed, and that 1 over n h over k is bigger than h minus delta. So 20 and 21 together also ensures that for sufficient large block lengths n, that that entropy of k over n minus entropy of L over n is smaller equal to epsilon. So they should be of the same size and both uniform. We define as UCR, so the uniform common randomness capacity, the maximum achievable uniform common randomness capacity. And we consider the maximum error probability criterion. Terminal R can communicate to B, as I told you before, an arbitrary single user channel W. And we find out that this UCR capacity is equal to the maximum of the mutual information between U and X And you see a very similar thing, like in the Alzheimer case, U, X, and Y form a Markov chain, and that the mutual information between U and X minus U and Y must be less or equal than the capacity of the channel, the transmission capacity of the channel. What do we use? We use the for the formula, we use the theorem of Verdu and Hahn, who shows that the general formula of the transmission capacity of an arbitrary channel W is equal to the subplenum over each T and the mutual information between T and Z. And the converse that K and L be permissible pairs, then we show that a function P can be mapped into a random variable K, satisfying K greater or equal by terminal A in the function lambda. These are all these functions. And we have to show that there exists an arbitrary large N such H over K is smaller or equal than our formula here for some alpha N, which are arbitrarily small. Then we generalize this for slow fading channels. So we looked at the slow fading channels for common randomness over a zero channel. So terminal A and B know the distribution of the gain G, and the receiver channel state information, sorry. We call it here RCSI. And again, we assume that we don't have available common randomness. So, and of course, we need some power constraint here to show that satisfies this probability distribution. And we get that an achievable outage from randomness capacity is defined, that's the definition of the achievable common randomness capacity. Again, like before, a number H is called an achievable outage from randomness capacity rate, if there exists a non-negative constant C, such that for every alpha and delta greater than 0, there exists a permissional pair of random variables K and L, such that the error probability is small and that this is a rate oscillate. And of course, the capacity is defined as the maximum achievable outage common randomness capacity. Then we have to define a code form for this common randomness capacity with decoding sets and this maximum, and we do it with maximum error probability with disjoint decoding sets with this power constraint here. So that's transmission code of length M1. Now for the achievable outage rate, R is defined as you expected as the scaling is here really normal, log gamma n over n. And now comes the theorem I want to show you. And here we have, we assume this channel state information and G of an arbitrary distribution, and then we show that we have this capacity for the single this single letter character. And the outage capacity is really, it's again very similar to the formula which is expected. In the sketch of the direct proof, we extend the proof of Alcide and Schaefer to the zero flow fading. We want to generate a nearly uniform random variable, and we consider a set of sequences Uij and map them by, so X is mapped by big T to Uij, and Uij, we choose Uij and X joint typically, and YZ is mapped to some estimate here. So it's a typical decoder and a typical encoder. And then for the converse, again, we have to show if you choose a permissional pair according to the CR generation, then it has to be smaller than this. So what we show, so feedback can increase the identification capacity, more noise increase the identification capacity. In many cases, the common randomness capacity is equal to the identification capacity, and common randomness increases the identification capacity as a result. Okay, we start now with part 4, embedded security. So if we look at the traditional security approach, normally we assume we have an encoder, a channel, and a decoder, and we have normal transmission here. And if you want to ensure security, so we assume we have a reliable bit type somehow, and we do some encryption and decryption. So the security is done somehow on the top. That's conditional security under certain assumptions. So perhaps complexity or limited computational power of the eavesdropper. Those things like RSR or something are used to generate the secret communication, or if both people have secret keys, you can do some security. But we want to do something different now. We look at embedded security. So we want to have integrated protocols on the physical layer for certain specified and guaranteed securities. So channels for transmission of messages and secret key generation. Our new concept is information theoretic security, also called physical layer security. So we want to design protocols for secret key generation or transmission, and what we use is the uncertainty at eve of the generated key or of the transmitted message, and new challenges. So channel uncertainty, certainties, varying resources, perhaps interference, quantification of resources, also adversarial effect. Just I remind you to the arbitrary varying channel and the jammer. Networks with legitimate and non-legitimate receivers. So let's look at the model. The first model we looked at is the following. We have somehow, it looks a little bit like broadcast channel. We have here the sender, Alice, and she sends this message over this channel. And here we have a legal receiver, and here we have a non-legal receiver. So here we have Bob, and here we have me. Both receive something, and what we want somehow, we do the very simple assumption. We model the simplest model first. So we assume that we have a discrete randomness broadcast channel here. So again, I remind you that means that the transmission probabilities are memoryless, so we can write every symbol as a product here, and this holds for the channel W and also for the channel V. And we assume that Eve is passive, so she does anything. She just listens to the channel and tries to interrupt the communication. And our goal is now to transmit the message M reliable to the legal receiver, and while keeping Eve ignorant. And you see, what does it mean? Our assumption is here that the mutual information between M and ZM goes to 0. That means Eve cannot do anything, so I have no clue what it is. So that's a strong secrecy requirement that the mutual information between M and ZM goes to 0. And it was already shown for this model that the secrecy capacity of the wiretapper is equal to the mutual information between U and Y minus the mutual information between U and Z, where U X and Z form a Markov chain. This was a result of Schaefer who looked exactly at this model. The first idea was by Weiner, who looked at the degraded case. That means first Alice sends a message to Bob, and behind Bob, for some reason, there is sitting Eve, who can have an extra channel after it was transmitted to Bob and can look at it. Here you see what you have to assume is, of course, that this channel is somehow further than this channel. So the channel capacity of this channel must be bigger than the channel capacity of the channel VN. And you see that's very natural, the result. Somehow it's not really exactly the result, but you see somehow that you have here the capacity of the legal channel minus the capacity of the illegal channel. I think that's a very intuitive that you get such a result. But this is only for transmission. And now, since we are doing Post-Shannon theory, we compare this situation here for transmission, where Bob asks what is the message and Eve asks what is the message, to the situation for identification. So that means we have now the situation that Alice wants to send an identity to Bob, and he wants to know, is it my identity? But now we have an eavesdropper, and he's also interested in any other perhaps in the same identity as Bob, but can also another one, and ask, is it my identity? That's the goal of the eavesdropper now. So Alice has to transmit a message to the legal receiver Bob. Bob is interested in the message M prime, and he has to decide if M prime is transmitted or not. And Alice has no knowledge about M prime. The non-legal receiver E is not able to identify any message. That should be our goal. So here you have again the system model with Alice, Bob, and E. So, okay, we can define it in the following way. So we do it randomized. So again, for deterministic, it doesn't make so much sense if you do not restrict, do not add some additional constraints. So we have to use randomized. We will look at randomized identification. So we will to construct a randomized identification code for wiretap channel. So again, we have a pair, QI, DI, QI probability distribution, we have decoding sets, DI, they have not to be disjoint, and for all i's from 1 to n, these are the messages, and for all IG in R1 to n, we have two conditions here. This is again the error of the first kind, and this is the error of the second kind. Here, for simplicity, we assume that they are the same. So before I denote this by lambda 1 and this by lambda 2. This comes from the channel noise, and this comes from the decoding scheme. And now our security assumption is now in the same way, is now as follows, that the error of Eve, errors of the first kind, also and error of the second kind, the summation of these two errors sums up to something which is bigger than 1 minus 1. So that means Eve cannot identify anything, but Bob can do it with error probability lambda. And Alcide and Chang, they showed, again, a very surprising result first, is the following. So if C is the channel capacity of the channel W, and CS is the secret transmission capacity of the wiretap channel, then the secret identification capacity is equal to the channel capacity. Again, we look at the double exponential case, so our scaling is again 2 to the NR. If the secret transmission capacity is bigger than 0, otherwise it's 0. What does it mean? So if we know that we can transmit something with positive capacity over the channel, then there's no difference if you look at the capacity, if you have a wiretap or not. It's only 0 if we cannot transmit anything secure. Just as a reminder here, so so we can write it In this way, the CSID is the maximum over X and the mutual information. If this is the formula for, if this is positive, then CS is bigger than 0 and 0 also. How can this happen? So again, we have to think about how we construct identification code. And again, we go back to our coloring. And you have to see, so here I take square root n like Alfred did, that's the square root n trick, but we also can divide it before I do divided the n, but you can also do it in this way. You will get the same result. So what you do again, you use the transmission code C prime just to transmit this coloring here, this first part of the message here, with the first n bits. And then, if you evaluate the coloring, that's the only part where we need really security. Because this first part is even chosen randomly. So Eve cannot learn anything from this. So we only have to secure this part here. And what do we know about this part? This part has capacity 0. And of course, then, if this part has capacity 0, and we use here wiretap code, we don't not lose anything. That's the reason why we have this result here. So just to send the evaluation of the function, if you remember, it was Ti of the randomly chosen L, which the L is chosen is sent here, and the Ti of L is transmitted here, and just here we need the wiretap. And because it's of capacity 0, square root of n, it's R0. So our coding length is here n plus square root of n, and it's, if you do it, analyze it asymptotically, it's the same if we look at the code of length n. That's the reason why I should there is a square root n and codes this square root n. And of course, now we ask what happens if we generalize this to a Gaussian channel. Yeah, again, we do it like before. We look again in such broadcasting case, but now again, we have Gaussian noise somehow here, and we look at W and V, that's the legal channel, that's the illegal channel. We assume there's the same alphabet here, and we call this channel W, V, G, G prime, and if C is G, G prime of P is the secrecy capacity of the channel, then for transmitting, we know that we have this result. That's just putting in what we have before. Somehow it's the same result or very similar result. That's the capacity of the legal channel. That's the capacity of the illegal channel. And it's only okay if the legal channel has a bigger capacity. Oh, that's wrong. So the legal channel should, I'm not okay, it's okay. It's the noise of the illegal channel is bigger than the noise of the illegal channel. Only then it works. That's a result for secret capacity. And now, if you generalize it for identification, you already will, perhaps now we get the same result, a very similar result. You see here the secure identification capacity of this Gaussian channel is equal to the transmission capacity if the secure capacity is bigger than 0, and it's 0 if we cannot transmit something securely. And the proof is very similar. We have to define again a wiretap code here for this. It's a transmission code, NN lambda wiretap code. It's a family of pairs. So you see we need here also for wiretap code, we read random encodings. That's the reason why we cannot do it with any additional assumption for deterministic identification. We need also for wiretap code some randomized encoding here. And we know for wiretap code, of course, the decoding sets have to be disjoint. And you see we have here error of the first kind, as usual, because we do transmission here. And we also have additional the secrecy constraint here. We want that Eve cannot decode anything. And if you look at the wiretap ID code, again, we have to do it, use a randomized code here. Here, the difference is now that, of course, we have to use a power constraint here, and we have the error of the first kind, error of the second kind, and we have this error, so the secrecy constraints here, that's the error of the first kind of Eve, that's the error of the second kind of Eve, and the sum of both have to be greater or equal than 1 minus none. This is a randomized wiretap ID code. And we have to consider these two statements, of course. So I want to give you now the idea of the proof. So we know if you can transmit something secure over the channel, then we know that the secure capacity is smaller or equal than the identification capacity. But this is clear, because if you just have a legal channel, then if you have this additional wiretap channel, then this cannot be legal. So this is the converse part, of course. And the main thing, the only thing where we have to work a little bit is if we cannot transmit anything secure, we have to show that we cannot also transmit an identity secure over the channel. And what we do, we instead of showing this, we show if the identity is if the secure identification capacity is greater than 0, then also the secure transmission capacity is greater than 0. So we assume now that this is greater than 0. This implies the existence of a wiretap code with positive range. So first we have to show that they exist. I remind you which were the definitions, because there exists such a code. We know we find such a QI, such that the error of the first kind is smaller than number, the error of the second kind is smaller than number, and that the security criterion is fulfilled. And we use the following lemma, that's the generalization of one lemma of Altswede and Chang. If we have two distributions on Ym, then there exists a decoding set in such a way that Qiy of this V plus Qy2 of V is smaller than epsilon. And if U is a binary random variable, which is uniform distributed, and the transmission probability of Ym conditionally that U is equal Y, then we have that the mutual information of U and Y is greater or equal than this is a binary entropy of 1/2 times 1 minus epsilon. And the second lemma says if we have two distributions on e to the n for any e on which is subset of Zn, then we have that QZ1 of E plus QZ2 plus E complement is greater than 1 minus epsilon. And if U is a random variable, then we can do the estimation in the other direction, so that the mutual information between U and Zn is lesser or equal than the infimum of all x between 0 and 1 minus and 2 over epsilon of q over x plus log of 1 over 1 minus x times epsilon. And with this lemma, we can prove together with the data processing inequality, we can prove that really the mutual information between U and Y is bigger than the mutual information between U and Z, and therefore our converse is done. Now, we don't have only illegal people will just listen to the channel. It might be, let's first not speak about people, let's speak about uncertainty of the channel. So perhaps we don't know what is the channel. Normally we send perhaps a pilot signal, and then we know the channel, can estimate it and start our protocol. And until now, I always assumed something like this is true, and the channel is very stable, at least for the next n days. But perhaps there's really some uncertainty because of the nature of the wireless channel, and perhaps the estimation on the pilot symbol is inaccurate. So we want to have now a code which works if, even for several channels. So even if the channel change, it should work. So a perfect CSI is really a challenging task. Eve will not show it channel state information to Alice to make it to the eavesdropper hardware. And perfect eavesdropper with CSI is more than questionable. So we consider now an uncertainty model in the following way. Now we assume here that the channel really can change. That's the so-called compound weighted channel. That means we have set S, and this set S is known to all, but it's not known which S is selected. This is unknown to Alice and Bob. So somehow they don't know the state of this channel. And the state causes here different channels W and different channels E. And now we want to find a formula for this system model. So in principle, we define a compound biotech channel by this family of channels, W and V, and W is this here and V is this here. So first, let's look what is known for the transmission case. So the single letter capacity is only known for special cases. But for the general characterization, you only have this multi-letter formula. This one here. So you see again a very similar behavior, because this is more or less, this is a capacity of the legal channel, and this is a capacity of the illegal channel. Now, we don't look at the normalization, but possibly if you put it in here and such things, what is not possible because of this maximization, but approximately you have the same behavior like expected. And because of this dependency of the block length n, it's really hard to evaluate. What happens now for robust identification? And we get a very similar result like before. So again, if you look now at the compound channel and look at the secrecy capacity of the compound channel, then you see that it's really to the transmission capacity. The secrecy capacity is bigger than 0. And it's equal to 0 if this is not, if this is equal to 0. It's a very nice thing because you see this formula is single letter, but this here is very complicated. It's a non-single letters formula. So sometimes it's easier to calculate the capacity as to decide it if it's 0 or it is to the capacity. And the idea of the proof is, again, might know, very similar to the previous case I showed you. So what do we have? What is our conclusion now? If we look at the transmission with the channel picture, we have here this part with local randomness, we have the channel, the wiretapper's goal, what is the message, and the receiver's goal, what is the message. And here we have identification. Sender chooses something, we have local randomness, and we have this nice formula if, so this is for the deterministic case, if the secrecy capacity is bigger than 0. So the goals are really what is the message, wiretapper's goal, ask for a message, receiver's goal. So we get exponential performance increase, and somehow we pay no price capacity-wise for security. Of course, you can also, it's not on the slides here, this JAMA model, which I showed you before, which is a little bit more tricky than the compound channel, where at every instance, every send symbol, the JAMA can change something. This is also known, and there you get again a similar result. There you get more problems because you have to avoid that something is symmetrizable, but we can create randomness, and it's not so easy. So we need, in this case, you get a formula where you have 0 because the channel is symmetrizable, or you have 0 because the secure, it's not possible to transmit a message securely. Okay, let's continue with part 5. It's further implementation and identification in networks. Let's first start with a small example where we also looked at it and looked at the system model and analyzed it, and also other people did this already. So we look at the following model, you know it as before. Now we look at the broadcast channel. Before, you know, you have the wiretap channel where you have legal and illegal. So receiver. Now we look at the broadcast channel. In this case, you have 2 legal receivers, and both want to know, this one is I1 is sent, this one wants to know I2 is sent. And so we have these 2 decoders interested in 2 different messages. Yes, and the encoder included I1 and I2. Here I already put the more general model, the compound channel. So here again, like before, we have the situation that we don't know which kind of channels are going to decoder 2 and decoder 1. So one channel is selected from a set of channels. Perhaps the compound channel for receiver 1 and 2, we have W1 and W2, perhaps unknown because of fading or other situations. And then, of course, an N and 1 and 2 ID code is a family of such triples here. So we need, again, randomized encoding. And we have here the decoding sets for decoder 1, and here's the decoding set for decoder 2. And you have to define the N and 1 and 2 lambda code. I don't distinguish here between errors of the first and the second kind. I found them both here by lambda. And there are 2 ways to consider the situation. One thing is that you said you have an unknown message distribution. This is done by Alswede in his paper of general theory of information transfer updated. Or you say you already have a uniform message distribution. That means you already have some randomness in the distribution of your message. Then here I call it IBM code. So we have to maximize over the messages. And here it's an IDA code. So irrelevant messages are randomness. No more randomness is needed in this case. And here you see you have your averaging, and here you can't averaging because you look at maximal error. So these pairs are ID code, and here you have this as an NN1 lambda ID code. You see a lambda 1 and lambda 2. In our assumption at just the same value, of course, you can do it also with different lambda 1 and lambda 2, but we want to have that both are small. One surprising thing is that the capacity do not change if the message set are degraded. So as I told you, there's a result of Alswede in general information transfer updated, and then of Rafa and Lapidot. And we looked at the case of a compound channel. So we calculate the capacity for compound channel and also for MIMO broadcast channel. Okay, before I come to the next page, but let me say something about this. So of course it's also generalized for MAX. for the multiple access channel where you have two senders and one receiver. There's also the case that it also depends, the capacity depends if the perhaps the two senders are cooperate or not. And in general, there's also, of course, you can also assume in a network, here all things I presented you, the receiver and the sender trust each other. So what is also possible, there are already works where receiver and senders don't trust each other. Perhaps in the networks, that's a reasonable assumption that you have perhaps some malicious sender or malicious receiver who don't follow the protocol. All the things I presented you in this tutorial today just assumed that everyone is following the protocol. And of course it makes sense also to look at the case when this is not the case. So that means that's called oblivious transfer or commitment transmission. There exist already some works, and also in our program we already looked at this and worked on this, but somehow because of some time constraint I didn't add this to this tutorial. I think it's a tutorial in itself to tell people about this thing. Finally, I want to tell you first why we are motivated in this project. So it was motivated by a project. It's called 6G Live. So, and the 6G Live project is a joint project between the Technical University of Munich and the Technical University of Dresden. It started in August, 15th of August 2021, and 70 million for 4 years. We have 60 PIs and 126 researchers. Fitzek, Boche, and Keller are the leaders somehow. And we are focusing on human their communication in interaction with their machines and the virtual world. So we looked at digital transfer, and you see the four key performance indicators are latency, resilience, security, and sustainability. And of course, in this project, before I come to this project and how Post-Shannon goes in it, I will tell you something about the evolution of communication networks. So here you see the first network here with a telephone. So our telephone network here, the goal was just that we have two parties and they want to communicate with each other. Then this network was somehow extended by the internet. So here you see it was with fixed places and voice, and then it was extended with mobile communication, and it was main thing with data. So the internet was built. So that was the next step of communication, and the network already had inside some intelligence. So the third step is now the future step, where we want to look at the Internet of Things. So we have voice, we have data, and we have also some control. So we want to control cars with the net. Everything, that's also one goal in 6G. Every network should be included, not only mobile network. And a lot of things are done by softwareization. So, for example, we want that the network can compute something in the internet. That's also one thing. And for this softwareization, we can use also the Post-Shannon theory. We heard about this today. So here you see some pictures of important people. So to the left, Post-Shannon. His name was mentioned many times in this tutorial, and he somehow calculates the limits of communication over channels, and that was his main contribution here. And then, of course, all his theories are also basics for the Post-Shannon theory. Then you see perhaps here the most unknown one, that's Paul Barron. He somehow created networks already in the 60s and asked very important questions. So about resilience, energy, and cost constraint. He already looked at networks which also want communicate data over the networks, and if people move and are not in fixed places. And finally, now also Alan Turing come into the game when we want to compute something, and his theory is somehow the basic for all this computing things we want to do in the networks. So what can we do when we use this softwareization? So one thing we can of course do, what you see here, we can build resilience. We can reduce latency. For example, we can have resilience here by multiple passes. And we can have resilience by distributed storage and distributed computing, which is based on coding. And of course, what can we improve in 6G? One thing is, of course, we can have novel architecture. So what does it mean? So if you look at the developments here, you have many steps. You start with 1G, 3G, 4G, and now you see already the difference. Now in 5G, we have many releases, and this gives us the possibility also to add something. And then we also have some special nodes like 5G campus, where we want to have an island, a network island, which is built for some industry or something. And what they use all these islands and all the things what come always more into play is open radio access networks. So the core, of course, is the second important thing here in 6G, but this is more or less realized in softwareization. And one goal is, of course, also to fully realize, partially it's already done, this open radio access network in software. And all of this developments should go not to a new 5G release. At one point, we make a step to 6G. And there we want to build networks with a special task. So in 5G, it's more about machine-to-machine communication. So 6G is more focused, even if it's already part of 5G, but this is more focused on human-to-machine communication. What can human and machines do together? That's the question. And therefore, one thing we need for this is perhaps the Post-Shannon theory. And here, prelude already, we talked a little bit like this, we call it Post-Shannon theory, but already Shannon and Weaver, they wrote a book together in 1964 about conveying information between the sender and the receiver. They have three levels. They speak about level A, level B, and level C. And level A is a technical problem. How accurately can the symbol of communication be transmitted? And this is somehow what we now call Shannon theory, and what we realized already, and that's already the known part. But then they also have level B and level C. And level B is a semantic problem. How precisely do the transmitted symbol convey the desired meaning? So not only that the sender want to know which message was received, perhaps you want to receive the same symbols, but perhaps we just want to know some meaning, and does it work correctly? And that comes together with the effectiveness problem. How effectively does the received meaning affect conduct in the desired way? That means perhaps the receiver only, like in identification, want to know, is a special message received or not? And then it makes no sense to do the full communication, and we are immediately at the model of identification, what you have seen a lot of times in this tutorial already. And there's an early paper of Fitzek already in 2006. And it was called Medium is a Message. And there, without knowing it, he considered already goal-oriented randomization. So because what he recognized that he comes about, somehow he comes over, or he got some capacity to join Shannon. And he told us that there was a lot of discussion with his colleague, how is it possible? And the reason was really that his communication was goal-oriented. So, and somehow he already it was a very practical model, and he already has a feeling there is something. Here's some example where we can use post-Shannon theory. For example, for a digital twin, we have it perhaps already in 5G, but perhaps we have a more advanced one in 6G, and where we want perhaps to have a robot which can learn certain things, and we have to do some exchange between the real system and the digital twin. And how we should do this. So, for example, if we have a lot of many possible states perhaps of the system. Let's assume that these are 2 to the 1,000 states. So if we want to know the exact states here at the digital twin, we need 1,000 bits. But if we just want to identify in which is a digital twin in this state, yes or not, then we have, if we just use this double exponential donors, then we need about 10 bits just to check if it's in the correct state, yes or no. So we don't have to communicate this 1,000 bits. So this cross verifying is really important. Of course, if the digital twin then knows, oh, there's some error, he's not in the state what I have expected, I need the correct state, then of course we have to do the Shannon transition. So there's no way to get rid. Sometimes I was asked if post-Shannon can we then throw away the normal communication? Of course not, because a lot of times we have the goal to get the whole message. So in this case, then we have to do the things. But if it's matched, then we are fine for our visit and we do nothing, and that's very good somehow. Crucial thing really is randomness. And the question is, of course, how do we create randomness? As you see here, there are a lot of randomized, pseudo random generators you see here. And also there are seeds for common randomness. So that means you have a small seed and can create a lot of common randomness with a pseudo random generator. So unfortunately, they are not theoretically so. Yeah, they do not so much theoretical research on it, so we cannot really prove something with it, but they work further well. So as an example, here we have different resources for randomness. For here, IETF, or here some Fibonacci-based. And the question is, of course, somehow, how good is the randomness? How can we create the randomness? And can we do it effectively? And one way, I didn't talk about this, is, of course, quantum. With an underlying quantum communication network, you can create local randomness. If you have, perhaps include later in 6G a quantum communication network, then you can use it at your position to create here, this picture shows local randomness. You can create it with quantum. You can buy some cards already for computers, insert it, and get some quantum randomness. So the question is, of course, how fast it is. At the moment, they are not so fast as the pseudo random generator, but perhaps they will be good. So you see here this randomness. And perhaps it would be nice also to have an underlying communication network with entanglement. If you know entanglement, with entanglement, you can create from randomness. And if you have a layer where you can create entanglement, of course, there are still a lot of problems in networks. So you cannot store the qubits so long, and there are a lot of problems. But perhaps we can create this. And if you have entanglement between 2 points, then you can immediately get common randomness from it. So that might be one goal, and that would be nice if we can also use these sources for post-Shannon theory, of course. There are already some books, so which are written by the people of this tutorial are involved in it. You see, there's a book about novel architectures and softwareized networks. So there, Fitzek is somehow the experts in it. So there are some human, machine, and cohabitants. So there's something about the tactile internet. So Frank and Holger are the experts in this also. And then there's a book on post-Shannon theory. You see a book, and this is a book, or this is somehow perhaps it's a lecture which was given by Rudolf Alswede around, I don't know, 2001 or 2002. And I was a PhD student of Rudolf Alswede, and he left us with about, I think, 4,000 pages of lecture notes. And now we already published 6 books from these lecture notes, and it's very interesting. And the 6th volume is of identification and other probabilistic models. So it includes a lot of the theory of identification you find there. And then we wrote a book together, all together. So I think all people of this tutorial, or only Rafael not, but most of the people of the tutorial are involved in this book. It's on quantum communication networks. So in this book, somehow we write about the basis to have communication networks with a quantum layer. What can we do with it, and what is possible with it? So this might be 2 or 4 interesting books for you to read and to look. And with this, let's just have a look what we have in part 5. I show you that method identification can result in a significant performance gain, and that the performance task identification forms an actual basis for the area of the tactile internet for machine-to-machine communication and for machine-to-human communication. And I didn't go into details, but you can think about the vehicle communication might be also an application of identification when you just want to identify is one car crossing my line, yes or no. And secure identification forms the basis for provable secure communication and storage for protection of privacy. So that finished somehow our tutorial. So we thank all supporters which support our work here. You see here the DFG project, and you see here there's a BMBF project. It's called Newcom, where we also work a lot of post-Shannon theory. You see here projects of Holger Boche, a project of myself, and a project of Rafael Schaefer. And then there's, of course, this Mamoko project. I have a small section where I showed you that molecular communication is also related to post-Shannon theory. And of course, finally, we thank our 6G Live project. It gives the biggest support perhaps because we have a lot of PhD students working in 6G Live, a lot of exchange with people from practice and theory. And I hope you enjoy the video presentation of this tutorial. Perhaps I can see you live also in Rio. Okay, thank you and goodbye.